Right now, somewhere on Earth, there is a group of people, just human beings in these white clean room suits and safety goggles. And they are trying to build a cage out of invisible magnetic fields.
Right, which is, I mean, it's a staggering concept when you really pause to think about it.
It really is.
Yeah.
Their ultimate goal is to trap a piece of a star. And this is happening in these facilities nestled against quiet hillsides, right down the hall from, mundane cafeterias and employee parking lots.
Exactly, and inside those walls, they are recreating conditions that simply haven't existed since the dawn of the cosmos.
Yeah. They are generating temperatures 10 times hotter than the center of our sun. I mean, think about that for a second. We are a species of bipedal primates. We are bound to the gravity of this humid blue rock, and yet our ultimate quest, our defining technological crusade, is to steal the primordial fire of the heavens.
And not just steal it, but force it to burn safely and endlessly inside a metal box.
Right. So today, you are listening to a deep dive into what I honestly believe is the defining struggle of human history. Because this isn't a chronicle of a war fought against rival nations or, armies equipped with gunpowder and steel.
No, this is a story of an epic, brutal, and just profoundly beautiful war against the fundamental laws of physics.
We are looking at the impossible science of nuclear fusion. So, okay, let's unpack this, because I think when we say the words nuclear energy, most people immediately think of cooling towers, glowing green rods, and the specter of radioactive fallout.
Right, the classic Cold War imagery.
Yeah, exactly. But that is an entirely different beast, isn't it?
It absolutely is. And what's fascinating here is how completely opposite those two processes are. I mean, despite both operating at the microscopic atomic level.
Okay, so walk us through that. What is the fundamental difference?
Well, to truly grasp the titanic scale of what we are trying to achieve with fusion, you have to understand the nature of the enemy and the tools we've used in the past. The history of the atomic age, as you know it, the history that really dominated the 20th century, it began with destruction.
Right, the atomic bomb, fission.
Exactly. It began with breaking things apart. That is fission. I want you to imagine a universe populated by heavy, bloated, incredibly fragile giants.
Okay.
These are massive, unstable atoms like uranium-235 or plutonium. Their nuclei are just so overstuffed with protons and neutrons that they are constantly teetering on the absolute edge of collapse.
So they are barely holding themselves together as it is.
Precisely. So if you take a single, solitary, slow-moving neutron and you just toss it at one of these atomic giants, it acts like the final grain of sand that triggers a massive landslide.
It just shatters.
The uranium atom violently fractures, yes. It splits into two smaller, lighter elements. But in that catastrophic fracturing, it releases this tremendous burst of energy along with a few more stray neutrons.
And those stray neutrons are the problem, right? Because they act like shrapnel.
Exactly like shrapnel. Those strays fly outward, they strike neighboring uranium atoms, which in turn shatter, releasing even more energy and more neutrons. It is a volatile, self-sustaining chain reaction.
So fission is essentially taking a massive, unstable rock, teetering on the edge of a cliff, giving it a slight shove, and harnessing the raw energy of the avalanche.
That's a perfect analogy. It's effective, but it is inherently a process of decay and division. And it leaves behind fragments, this long-lived radioactive waste that remain toxic to living biology for, well, tens of thousands of years.
Right. It's a brilliant discovery, but it's ultimately the domain of radioactive chaos.
Yes. But fusion is something else entirely. If fission is breaking a giant apart, fusion is the pure act of creation.
The act of creation. I love that framing. So how does that work?
It is the engine that powers the entire universe. Every star you see in the night sky, including our own sun, is a colossal fusion reactor.
Okay, so instead of breaking heavy things, we are combining light things.
Exactly. The process involves taking the absolute lightest elements in existence, specifically isotopes of hydrogen, and forcing them together with such unimaginable violence that they merge to become an entirely new, heavier element like helium.
And that merging process is what releases the energy.
Yes. When they forge this new union, a tiny, tiny fraction of their mass is converted directly into pure energy. And I mean pure energy, dictated by Einstein's famous equation, E equals mc squared.
So a little bit of mass equals a terrifying amount of energy.
A truly staggering amount. The energy released by fusion makes the energy of fission look pale and honestly inefficient by comparison.
But there's a catch, obviously. If it were easy, we would have done it in the 60s.
There is a massive catch. The universe is a profoundly jealous guardian of this power. It strictly forbids this act of creation under normal earthly circumstances.
Right, because atoms naturally want to stay away from each other.
Yes, there is a fundamental invisible shield that protects atoms from one another. We call it Coulomb repulsion.
Okay, let me try to ground this for you, the listener, because the nucleus of an atom, the core, is packed with positively charged protons. And, as anyone who has ever played with magnets knows, if you take two positive charges, like two north poles, and try to push them together, they fight back.
They absolutely repel each other.
Yeah.
Yeah.
If you take two incredibly powerful neodymium magnets, the shiny silver ones, and you try to force their north poles to touch, you can actually feel this invisible, gelatinous wall of force pushing your hands apart.
It's a very physical sensation.
It is. If you push harder, the magnets will literally slip sideways to avoid touching. It physically hurts your hands to try and maintain that pressure. And that's just a couple of little magnets you can hold in your palm.
Yeah.
What are we dealing with at the atomic level?
You need to multiply that sensation you feel with the magnets by an astronomical factor. Coulomb repulsion is an electromagnetic wall of force that is exponentially stronger than gravity. The closer those two positively charged nuclei get to each other, the harder that invisible wall pushes back. It is a sheer exponential resistance.
So to achieve fusion, you have to force these two atoms together so tightly and so fast that you literally breach that wall.
Yes, you have to get them infinitesimally close, within a fraction of a trillionth of a millimeter.
A trillionth of a millimeter. That is incomprehensible.
It is, but you have to do it because if you can push them just past that electrostatic barrier, a different, more ancient rule of physics takes over, and that is the strong nuclear force.
The strong nuclear force, what does that do?
It is the glue that holds the universe together, but it has an incredibly short reach. It is like microscopic Velcro. It only works if the two pieces are literally physically touching.
So if you can overcome that tremendous magnetic repulsion and slam the nuclei into the domain of the strong nuclear force, they just snap together.
Exactly. They snap together, they fuse, and they release a tidal wave of clean energy.
Which I think raises a really important question for anyone listening. If it is so incredibly difficult, if the universe fights us every step of the way with an invisible wall of infinite repulsion, why do we bother?
That is the multi-billion-dollar question.
Right. Why are we dedicating decades of research, billions of dollars, and the brilliant minds of generations of scientists to this microscopic war? We already have solar power, we have wind, and yes, we have traditional nuclear fission. Why sacrifice the sanity of our best engineers on this crusade?
Because, simply put, the ultimate prize of this war is energy immortality.
Energy immortality.
Yes. If we connect this to the bigger picture, humanity's energy consumption is a relentless, ever-expanding curve. Historically, we have sustained ourselves by essentially burning the flesh of the earth, coal, oil, natural gas.
And we have terraformed our own atmosphere with carbon in the process.
Precisely. And while traditional nuclear fission is incredibly energy-dense and carbon-free, it leaves us with the geopolitical nightmare of managing highly radioactive waste for millennia.
So fusion is the silver bullet.
Fusion offers an absolute paradigm shift because the fuel for fusion doesn't require deep shaft mining or environmentally devastating extraction. We primarily use two isotopes of hydrogen, deuterium, and tritium.
And where do we get those?
Deuterium is naturally occurring in seawater. Roughly 1 in every 6,000 hydrogen atoms in the ocean is a deuterium atom.
Wait, so the fuel is just in the ocean?
Yes. We have enough deuterium in the Earth's oceans to power human civilization at its current massive energy appetite for literally billions of years.
That is insane. What about the other one, tritium?
Tritium can actually be bred within the reactor itself from lithium, which is incredibly abundant in the Earth's crust. So fuel scarcity becomes a thing of the past.
And what about safety? People hear nuclear and they think Chernobyl.
Fusion is inherently safe. That is the beauty of it. There is absolutely no possibility of a runaway chain reaction, no chance of a meltdown like Chernobyl or Fukushima.
I don't know.
Because the environment required for fusion is so extreme, it's actually incredibly fragile. If the reactor is breached, or if the magnetic cage fails, the plasma simply expands, it cools instantly, and the fusion reaction dies in a fraction of a second. It is a fragile fire.
So it wants to turn itself off.
Exactly. And the primary byproduct of all this, helium, an inert, harmless gas. The promise of fusion is limitless, perfectly clean, infinitely sustainable energy. It is the final answer to our energy crisis.
But there's always a but.
There is. To unlock this utopia, we have to learn to walk through hell. We have to tame the most violent, hostile, and chaotic environment in the architecture of the universe.
We had to awaken the fourth state of matter.
Yes, plasma.
Okay, here's where it gets really interesting. Because to build a star on Earth, you obviously cannot use the building blocks of ordinary reality.
No, you can't.
Right? If we want to hold something that is burning at 100 million degrees, we can't use solid metal. I don't care what miraculous titanium alloy you forge, it would vaporize instantly.
It would be gone in a microsecond.
Right. We can't use liquids, and we can't use a standard gas. Because solid, liquid, and gas, those three states of matter, they are docile slaves to earthly temperatures. They play by the peaceful rules of basic chemistry.
But fusion does not play by peaceful rules.
Exactly. If you want to ignite the cosmos inside a reactor chamber, you have to summon a storm. You must create a plasma. So what exactly is it?
The plasma state is, quite literally, the anatomy of pure chaos. To understand it, you have to visualize what happens when you introduce godlike levels of thermal and kinetic energy into a mundane system.
Okay, let's visualize it.
Let's start with a normal gas, like a cloud of hydrogen. In a normal gas, atoms are like well-ordered miniature solar systems. You have a massive, dense nucleus at the center, surrounded by a perfectly choreographed cloud of electrons orbiting in mathematical harmony.
They are stable.
They are neutral, stable, and relatively peaceful. But as you start to turn up the heat, and I don't mean heating it in an oven, I mean injecting energy until the temperature reaches tens of millions of degrees, the kinetic energy becomes a destructive force.
The heat literally tears them apart.
Yes. The atoms begin to vibrate and careen into one another at hyperviolent speeds. The collisions become so catastrophic that the structural integrity of the atom fails. The electrons, those protective orbiting shields, are violently ripped away from the gravitational pull of their central nuclei.
So the gas becomes ionized.
Exactly. At that critical threshold, the matter transcends. It is no longer a collection of neutral atoms peacefully bouncing off each other. It transmutes into a swirling, electrified tempest.
So you have the cores and the electrons just flying around separately.
Yes, you now have a chaotic soup of bare, heavy nuclei, which are positively charged, and a swarm of incredibly agile free electrons, which are negatively charged. It flows and swirls like a fluid, but it is a living, electrified fluid.
Because every particle has a charge.
Exactly. And because they carry a charge, the entire cloud responds violently to electromagnetic fields. It rides, it twists, it generates its own internal electrical currents and magnetic anomalies. It acts like a predator trapped in a cage.
It sounds like an invisible apocalyptic dimension. But the truth is, I mean, you've seen this. Even if you aren't a physicist, you, the listener, have witnessed the majesty of the fourth state of matter.
You see it more often than you think.
Right. When a massive thunderstorm rolls in and a lightning bolt tears the sky apart, that blinding, jagged channel of white fire, that is plasma.
The colossal electrical discharge of the storm literally rips the electrons off the air molecules for a microscopic fraction of a second, ionizing the atmosphere.
And you've seen it if you've ever looked at the northern lights, too. The dancing ribbons of emerald, crimson, and violet in the auroras, that's plasma.
That is the electromagnetic breath of our sun, the solar winds slamming relentlessly into the Earth's invisible magnetic armor.
Yeah, the solar particles excite the gases in our high atmosphere. They rip electrons away and spark a cold, high-altitude plasma fire. We even trap it in glass tubes to light up our cities.
Right, like neon signs.
Exactly. The glowing, buzzing heart of a neon sign or a standard fluorescent tube in an office ceiling is a tightly controlled, low-temperature plasma. But the ultimate expression of this state, the terrifying extreme that we're trying to bottle up, is the sun itself.
Yes. If you could somehow survive the journey and dive into the core of our sun, you would be swimming in a spherical, monstrous ocean of pure, hyperdense plasma, held together only by the crushing fist of its own immense gravity.
But here's a crucial distinction that I think often gets overlooked, and it dictates the terms of our technological war here on Earth. In the mortal arena of fusion research, not all plasmas are created equal, right?
Oh, definitely not. The battlefield changes drastically depending on how successful you were at tearing those atoms apart in the first place. We have to draw an absolute line between two fronts, total ionization and partial ionization.
Okay, let's start with total ionization. What does that look like?
Total ionization is the absolute extreme. It is a state of fiery purity. In a totally ionized plasma, the energy injected is so astronomically high that the atomic annihilation is complete.
Complete annihilation.
Yes. Every single electron has been stripped from its host nucleus. There is not a single intact atom left in the entire volume. It is reduced to its primordial raw components, a blinding soup of bare positive nuclei and fast-moving negative electrons.
That sounds kind of simple, actually.
From a physics standpoint, it is actually somewhat beautiful. It is an open battlefield where the laws of pure electrodynamics govern without rival. It is mathematically clean, so to speak. We only have to calculate the interactions between free charges.
So total ionization sounds like the ideal scenario. You've completely cleared the board of any complicated structures. It's just pure raw charges interacting. So what happens if you don't achieve that? What is partial ionization? It sounds like a job left half finished.
Make no mistake, partial ionization is infinitely more treacherous. It is a labyrinth of shadows.
Why? What makes it so difficult?
Well, in a partially ionized plasma, the thermal energy hasn't achieved a total victory over the atomic architecture. The heat has freed many electrons, turning them into wandering mercenaries that zip through the void, but some electrons are incredibly stubborn.
Yes, they stay attached.
Yes, they remain deeply entrenched, clinging desperately to the inner orbital shells of their host atoms. This creates a war zone of terrifying complexity.
Because now you have a mix of everything.
Exactly. You have free-floating charges interacting wildly, but scattered throughout this ocean, you have floating islands of intact atomic structure. These are heavy ions that still possess layers of orbiting electrons acting like intact kappa galls.
And that messes up the math.
It defies even our most advanced supercomputers. You now have quantumly bound electrons coexisting with free, wandering electrons. They collide, they trade places, they exchange energy, and they constantly perturb the environment.
So it's unpredictable.
Deeply unpredictable. In this quantum fog of war, every time we fire a pulse of energy into the plasma to try and heat it, that energy doesn't just travel smoothly through free charges. It crashes into a thick minefield of entrenched electrons.
The bound ones.
Yes, these bound electrons absorb the energy, deflect it, and warp our calculations. This dark coexistence of free and bound states exponentially complicates every survival equation and every ballistic calculation our operators attempt.
Okay, so we've summoned the storm. We have this boiling, swirling, unpredictable plasma. But that brings us to what might be the most terrifying engineering hurdle in human history.
Confinement.
Exactly. Once you have a miniature piece of the sun burning inside your facility, how do you stop it from melting the steel walls of its prison? How do you prevent this tempest from instantly vaporizing the reactor? Or, conversely, how do you stop it from expanding so fast that it cools down and dies before it even has a chance to fuse?
We have to confine it. We have to forge cages capable of holding gods.
So how do we do it?
This is where theoretical physics hits the cold, hard reality of combat engineering. And the rules of this engagement are dictated by an unbreakable edict, a divine law written into the mathematics of the cosmos. It is called the Lawson criterion.
The Lawson criterion.
Yes, this isn't a mere suggestion or an engineering guideline. It is the absolute threshold between the life and death of an artificial star.
What are the rules?
For the fire of fusion to ignite, and more importantly, for it to become self-sustaining, meaning the energy it produces is enough to keep itself burning without us constantly pumping power into it. 3 massive elements must achieve perfect harmony.
Okay, what is the first pillar?
First, temperature. You must inject enough heat into the plasma to reach roughly 100 to 150 million degrees Celsius.
That is 10 times hotter than the core of our sun.
It is.
Why does it need to be so much hotter than the actual sun?
Because we don't have the gravitational crushing force of the sun, so we have to make up for it with sheer thermal speed. You must give the ions enough demented kinetic speed so that when they collide, they hit hard enough to shatter that Coulomb repulsion barrier we talked about earlier.
Got it. Speed equals heat. What's the second pillar?
Second, density. It is not enough to just have fast-moving ions. Space is incredibly vast at the atomic scale. If the plasma is too thin, these super-fast ions will just fly past each other in the dark and never collide.
So you have to pack them in tight.
You must pack them, compress them, and crush them into a space so tight that head-on collisions become mathematically unavoidable.
Okay, temperature and density. And the third?
The third, and honestly the cruelest element of all, confinement time.
Holding it together.
Yes, you must hold this nightmare of heat and density together, fighting against the plasma's natural explosive desire to expand and dissipate. You have to hold it long enough for the microscopic sparks of fusion to catch, for the nuclear chain to propagate, and for the energy output to exceed the energy input.
And what happens if you fail on just one of those metrics?
If a single one of these three pillars wobbles, if the temperature drops by a fraction, if the density loosens by a millimeter, if the confinement time falls short by a nanosecond, the star aborts. The plasma instantly cools. The mission fails completely.
It's an all-or-nothing game.
Absolutely.
And to try and satisfy this brutal, unforgiving law of the Lawson criterion, human ingenuity has essentially split into two monumental schools of thought, two entirely different philosophies of engineering, both attempting to reach the exact same summit.
Yes, magnetic and inertial.
Let's talk about the first path, the path of patience and the invisible embrace. We call it magnetic confinement.
This is what most people picture when they think of fusion reactor.
Right. Picture machines of mythological proportions, massive toroidal or, donut-shaped chambers known as tokamaks and accelerators. Inside these cathedrals of science, we don't try to physically touch the plasma. Instead, we weave a complex, invisible net of magnetic fields.
Because if the plasma touches the walls, it's game over.
Exactly. So outside the vacuum chamber, scientists build these gigantic superconducting electromagnets. And to make them superconductive, so they can carry massive electrical currents without melting, these magnets are bathed in liquid helium, bringing their temperature down to nearly absolute zero, about minus 269 degrees Celsius.
Which is a beautiful paradox in itself.
It really is. You have magnets that are among the coldest objects in the known universe, sitting just inches away from a plasma that is the hottest place in the solar system.
Yes.
These magnetic fields penetrate the vacuum chamber and grab the charged particles of the plasma. The ions and electrons are forced to spiral tightly along the magnetic field lines, basically levitating in the empty space, perfectly trapped, so they never actually touch the physical steel wall.
That's brilliant design. Yeah.
Magnetic confinement uses a very low-density plasma. It's almost like a ghost of a gas. But because the magnetic cage is so stable, they can hold the plasma for a relatively long time. We're talking seconds or even minutes. It is a slow, steady, controlled squeeze.
It is an elegant approach, but it requires unimaginable precision.
Why? Does the plasma fight back?
Always. Any slight instability in the magnetic field can cause the plasma to violently whip outward, touching the wall and instantly cooling the reaction, causing what we call a disruption.
A disruption? That sounds expensive.
Extremely. But then we have the second philosophy. If magnetic confinement is the slow, patient squeeze, inertial confinement is the realm of absolute, unbridled violence.
Oh, this is my favorite part.
It abandons long confinement times entirely. This is the realm of pure apocalyptic speed.
Well, so does it work?
In inertial confinement, we don't start with a giant cloud of plasma. We start with a tiny, perfectly machined sphere, a microscopic pearl of solid deuterium and tritium fuel, roughly the size of a single peppercorn.
A peppercorn.
Yes. We place this tiny grain of sand inside a small gold cylinder called a hohlraum, and then we unleash the wrath of the world upon it.
We fire lasers at it.
Not just lasers. Using facilities like the National Ignition Facility, we fire the most powerful laser arrays ever constructed. We're talking about hundreds of laser beams, perfectly synchronized, delivering trillions of watts of power in a fraction of a billionth of a second.
Trillions of watts.
Yes. The lasers hit the inside of the gold cylinder, converting instantly into a bath of intense X-rays. These X-rays blast the outer layer of our tiny fuel pellet. The outer layer vaporizes and explodes outward.
And because every action has an equal and opposite reaction.
Exactly. According to Newton's third law, as the outer shell explodes outward, it drives the inner core of the fuel inward. It is a rocket effect in reverse. It generates an imploding shockwave that crashes down on the center of the pellet, compressing the fuel to densities hundreds of times greater than solid lead.
That is terrifying.
The temperature spikes. For a fraction of an unfathomable nanosecond, the core ignites. The fusion happens so incredibly fast that the fuel's own inertia, its own sheer physical mass, doesn't have time to blow apart before the reaction finishes.
So the mass itself holds it together.
Yes. We compress a universe into the head of a pin faster than light can cross a drop of water.
Okay, stop right there. Because this is exactly where my mind hits a brick wall. And I guarantee you, the listener, is wondering the exact same thing right now.
What's the issue?
Let's really look at the logistics of this. We are firing the most powerful lasers in the world, or in some experimental designs, incredibly fast beams of heavy ions. We are firing these hyper-accelerated beams at a target the size of a peppercorn. And the entire process of compression and heating takes place in a fraction of a billionth of a second.
Right.
Wait, hold on. If the beam is traveling at nearly the speed of light, and the plasma target is less than a millimeter thick, how in the world does the beam actually transfer its destructive energy to the plasma? Shouldn't it just blast straight through?
It's a very fair question.
I mean, if I shoot a high-powered rifle at a curtain of smoke,
Hmm.
the bullet doesn't stop and deliver its energy to the smoke. It just rips a hole in it and keeps going. Why doesn't the laser pulse or the ion beam just pass right through the pellet, taking all its precious ignition energy with it and leaving our miniature star dead on arrival?
That right there. That is the exact paradox. You have articulated the abyss over which our engineers walk a tightrope every single day.
So I'm not crazy.
No, your intuition is absolutely correct. If that ion beam or laser pulse blasts cleanly through the fuel pearl and gets lost in the vacuum chamber, the Lawson criterion collapses instantly. The miracle evaporates.
So how do we stop it?
For the star to be born, the arrow, the ion beam must be caught. It must be violently arrested by the target. It must be forced to surrender, to bleed out every single drop of its kinetic energy directly into the heart of the plasma to heat it.
It has to hit the brakes.
Exactly. And this mystery of energy transfer, this desperate attempt to force the plasma to absorb the weapon's power, brings us to the absolute beating heart of our deep dive today. We are descending into the ultimate concept of this war. Welcome to the battle, stopping power.
Stopping power. The phrase itself sounds heavy. It sounds like an inescapable decree from the universe. The ion beam is our sacred lance, hurled at lethal velocity to pierce and compress the plasma. But the plasma isn't a passive victim. It doesn't just sit there and take the hit. That furious ionized deity fights back.
It resists with every charged particle in its being.
So how do we define stopping power?
Let's define this force with absolute clarity. In its mathematical, brutal essence, stopping power is a measure of inexorable exhaustion.
Exhaustion.
Yes. It represents the exact quantifiable amount of kinetic energy that a high-speed projectile like our charged particle loses for every microscopic fraction of distance it manages to penetrate through a medium. It is the blood tribute that the plasma extracts from the movement of our projectile.
Okay, let me try to translate this into an image that you, listening at home, can burn into your mind. Think of kinetic energy as the raw forward vitality, the sheer furious momentum of our ion projectile.
The energy of its motion.
Right. And think of the plasma it has to travel through as incredibly hostile enemy territory. Stopping power is essentially the mathematical rate at which our warrior's health bar drops as it pushes forward. It is, to borrow a concept from terrestrial engineering, a form of drag force, an extreme cosmic friction born of electromagnetism.
To truly visualize this clash of titans, you have to shrink your consciousness down and plunge with us into the microscopic ocean.
I am ready.
I want you to imagine that you are the projectile. You are a massive, heavy ion, perhaps a nucleus of argon or iron. You have been stripped of most of your electrons, leaving you with a massive positive charge.
Okay, I'm a positive heavy ion.
You have been accelerated down kilometers of vacuum tubing by powerful magnets until you are flying at a significant fraction of the speed of light. You are unimaginably heavy on the atomic scale, and you are brimming with lethal kinetic energy. Your final destination, the fusion target.
The peppercorn.
Yes. Suddenly the vacuum tube ends, you are fired. You plunge headfirst into the target, which, within a picosecond of you hitting it, flashes into a superheated plasma.
Okay.
It is like firing a solid steel cannonball at point-blank range into a dark, turbulent ocean. But this ocean isn't made of water. It is an ocean of magnetic anomalies, tidal waves of electric charges, thermal fury, and quantum chaos. And the absolute millisecond you pierce the surface of that ocean, the ocean begins to drag you down.
It's trying to stop me.
It starts to rob you of your momentum, trying to drown your speed and its vastness.
But wait, how exactly does it rob me of energy? There's no physical viscosity like honey or water, right?
Sure.
There's no thick air resistance. It's mostly empty space between atomic nuclei. Where does the friction actually come from in this atomic inferno?
The resistance isn't aerodynamic. It is purely electromagnetic. And it attacks you relentlessly from two entirely different fronts. The plasma uses two distinct strategies of warfare to bring you down.
What's the first front?
The first front is the battle against the free electrons. In the physics grimoires, this is known as the dielectric formalism.
Dielectric formalism.
Yes. As the colossal, positively charged ion tear the fabric of the plasma at inconceivable speeds, your intense positive charge severely disrupts the swarm of negative, free-floating electrons in the environment.
Because opposites attract.
Exactly. Because opposites attract. As you blast past them, you pull on them, they are irresistibly drawn toward your positive gravity. They try to swarm you, to envelop you. But you are traveling so incredibly fast that you leave them in the dust before they can actually latch onto you.
So they miss me.
They miss you, but their desperate lunge toward your flight path has created a localized distortion. You have essentially carved a phantom wake behind you, a dense wave of swarming electrons trailing you, much like the churning wake of white water behind a massive battleship slicing through the sea.
Okay, I see it.
And here's the trap. That phantom wake trailing behind you is composed of millions of negative electrons. It has a massive collective negative charge. And you are positive. So what does that wake do? It pulls backward on you. That retrospective attractive force, created entirely by your own high-speed passage, acts as a continuous invisible parachute. It constantly drags on you, draining your kinetic energy mile by microscopic mile.
That makes perfect sense. It's literally like a speedboat churning up a massive wave behind it, and the gravity of that wave pulling the boat backward.
Exactly.
But you said there were two fronts. That's just the free electrons. What's the second front?
The second front is much more direct and much more violent. Atomic excitations. Remember our discussion about partial ionization? We are rarely operating in a clean, totally ionized vacuum.
Right. There are intact atoms floating around.
Yes. As you struggle against the invisible drag of the wake behind you, you are also physically crashing into the heavy, intact ions lying in wait ahead of you. These are the atoms that still possess their thick armor of bound electrons.
So I'm crashing into their shields.
You smash directly into their electromagnetic shields. In every one of these high-speed proximity collisions, you are forced to pay a toll. You transfer a massive chunk of your raw kinetic energy into their bound electrons.
What happens to them?
You excite them. You violently bump these electrons up into higher quantum orbits, or, in the most savage impacts, you rip them completely off their host nucleus, contributing to the ionization of the plasma.
So that takes energy.
Every single blow you deliver, every quantum leap you force an electron to make, every shield you shatter requires energy, and that energy is subtracted directly from your velocity. Between the magnetic wake dragging you from behind and the atomic walls you are battering down in front of you, your speed is relentlessly sucked into the void.
Okay, here is where my common sense absolutely rebels, and I think anyone listening is going to feel the exact same way. Think about this logically. The human brain dictates that pushing through something hotter, denser, and more chaotic should require significantly more effort.
It seems intuitive.
Right. If I fire a bullet into a block of solid ice, it meets resistance. If I melt that ice into boiling water under high pressure, intuitive physics suggests the resistance should be comparable, if not higher, due to the chaotic movement of the boiling water. Logic dictates that a burning, turbulent plasma, a furious swarm of particles vibrating at millions of degrees, should be an infinitely harder barrier to pierce than a cold, orderly, dead gas. Isn't a literal wall of nuclear fire the ultimate defensive shield?
And there, in that perfectly logical assumption, is where the universe slaps us across the face with its paradoxical majesty.
Wait, I'm wrong.
This is the great plot twist of plasma physics. This is the phenomenon that leaves graduate students staring blankly at chalkboards and forces master physicists to rewrite their theoretical models. It is the great paradox of reduced stopping power.
Reduced stopping power, meaning it slows you down less.
Over the course of countless simulations and decades of experimental data paid for in sweat, blown budgets, and shattered diagnostic equipment, firing beams into plasmas of hydrogen and helium scientists observed something that defied all basic reason.
What did they see?
They discovered that under certain critical conditions, due to the extreme velocities involved and the unique vibrational frequencies of the plasma itself, a superheated, hyperdense plasma can actually offer less resistance to our projectile than a cold, dead, non-ionized gas.
Wait, what? Are you seriously telling me that it's physically easier to shoot a particle through the raging fury of a star than it is to shoot it through a cold cloud of gas?
Under the precise lens of quantum velocities, yes. Let's look at the cold gas first. In a cold gas, your projectile is blundering through a dense forest of intact atoms. It loses massive blocks of energy because it constantly has to pay the brutal toll of atomic excitation. It has to physically fight through the dense clouds of bound electrons.
Because none of them have been ripped off yet.
Exactly. But when that exact same gas is superheated into a plasma, when those electrons are liberated and become free-floating, something bizarre happens. The mathematics of resonance take over.
Resonance.
Remember the wake effect?
Yeah.
The drag caused by the free electrons trying to swarm behind the projectile? Well, how fast the plasma can react to form that wake is the limiting factor.
Well, because they are moving too fast.
Yes. In a superheated plasma, the free electrons are already moving at absolutely demented thermal speeds of their own. They are vibrating with so much heat energy that they are essentially buzzing around too erratically to organize.
They're too distracted.
If the plasma is hot enough and your projectile is fast enough, the free electrons literally cannot group together fast enough to form a coherent wake behind you. They are too chaotic to organize a coordinated drag force.
So they don't form the parachute.
They don't. So the massive ion projectile slips through, it cuts through the electrified net of the plasma with a lethal, frictionless grace, encountering significantly less total drag than it would in a cold environment. It glides through the madness with an unnatural, terrifying ease.
That is deeply counterintuitive, but I see the mechanism. The electrons are just too hot and distracted to grab onto the bullet. But wait, if the ion slips through the plasma more easily, that's a massive problem, isn't it?
It is an absolute operational nightmare. This revelation was both a triumph of scientific discovery and a crisis for reactor engineering.
Because we want it to stop.
Exactly. If the ion slips through the plasma with reduced resistance, it means it will penetrate much deeper into the target before it finally bleeds out its energy.
And if it goes too deep?
If it penetrates too far, it blasts right through the dense core of the fuel without heating it where it matters most. It deposits its precious ignition energy on the far side of the pellet, completely ruining the symmetrical implosion required for fusion.
So the star dies.
The star dies. This paradox forces the human operators of these experimental reactors to calculate their energy strikes with a precision that borders on divine precognition. They have to anticipate the exact degree of reduced stopping power. An infinitesimal error in that calculation means the lance passes cleanly through the heart, the star fails to ignite, and the multi-billion-dollar facility falls silent.
The precision you were talking about throws us directly into the fourth and perhaps most terrifying level of our descent today, the chaos of the void.
The statistical realm.
Yeah, because up until this point, we've been talking about this plasma ocean as if, despite being chaotic, it is mathematically uniform. We've been acting as if every single ion we fire into the target loses its energy by obeying the exact same law, marching to the exact same drumbeat toward its destination.
Which is completely false.
Right. The microscopic reality is much messier, much more disturbing, isn't it? The battlefield is not a flat, smooth plane. It is a writhing, living entity.
Exactly. Uniformity is a comforting illusion that physicists use to make the introductory equations solvable. But quantum reality is governed by absolute uncertainty and ruthless statistics. We now enter the domain of energy straggling.
Energy straggling. What does that mean in simple terms?
It means statistical fluctuations of energy loss. Imagine you have engineered the perfect particle accelerator. You fire a volley of exactly 1 million identical ions. They all possess the exact same mass. They are all charged with the exact same power. They are all moving at the absolutely identical, mathematically perfect speed. You aim them perfectly and fire them simultaneously into the flank of the plasma target.
Okay, a perfect volley.
If you could stand on the far side of the battlefield and measure every single one of those million ions as they emerged, you discover a horrifying truth. They have not lost the same amount of energy. Not a single individual ion will have the exact same remaining kinetic energy as its brother.
Let me paint a picture for the listener to really drive this madness home. Imagine an army of 1 million perfect Spartan warriors. They all weigh exactly the same. They wear identical armor. They have been trained to run at the exact same lethal, relentless pace.
Okay, I see where this is going.
Now, command them to charge blindly through a primordial ancient forest. It is pitch black, the trees are packed incredibly tight, and the terrain is completely unpredictable. It is a frantic, violent charge. Even though every single Spartan entered the tree line with the exact same speed and trajectory, their individual journeys are entirely dictated by the random chaos of the terrain.
The collisions.
Right. Some warriors, through sheer bad luck, will smash face first into thick oak trunks, breaking their bones and losing nearly all their momentum immediately. Others will trip over hidden root systems, falling into ravines, wasting precious seconds scrambling back up.
And a few will just glide through.
Exactly. A few lucky ones, favored by some capricious god of probability, will miraculously find narrow, clear paths through the dense underbrush, slipping between the trees without suffering a single scratch. When that army finally bursts out of the tree line on the other side, they are no longer a uniform, perfect force.
They are scattered.
They are scattered, they are disheveled. Some are crawling, dying from exhaustion, while others are still sprinting, full of vigor. They arrive at different times, possessing wildly different levels of vital energy. That dense, treacherous, unpredictable forest is the plasma. And that chaotic, scattered distribution of the soldier's vitality at the end of the run, that is energy straggling.
It is a brutal analogy, but it maps onto the physics with astonishing accuracy. Energy straggling is the universe's incessant reminder that at the atomic scale, individual destiny is ruled by random collision.
You just can't track them all.
You cannot track a single particle. You can only predict the probability of the swarm. And this scattered, arriving army infinitely complicates our ability to predict exactly where and when the maximum energy payload will be deposited into the heart of the fusion target.
So even if your calculations are perfect, chance can still ruin it?
Exactly. But as daunting as energy straggling is, there is one final monster lurking in the mathematics. It is the deepest layer of complexity, the final boss of plasma physics, which dictates whether we can actually predict any of this at all.
What is it?
It is the thermodynamic state of the plasma's soul. We call these the rules of the realm, and they are divided into two distinct doctrines, LTE and NLTE.
Okay, let's look at LTE first. What is it?
Local thermodynamic equilibrium. This is a state of ordered chaos. It is a hellscape, yes, but it is a hellscape that we have learned to comprehend.
How so?
In a state of LTE, the plasma is so incredibly dense and packed together that even light photons are trapped inside it. The atomic particles are smashing into each other so relentlessly, so overwhelmingly, that these mechanical collisions dictate all the rules of the system.
So the collisions are the dominant force.
Yes. In LTE, the local temperature acts as an absolute supreme dictator. It forces all the subatomic particles into a predictable mathematical distribution of energy. This distribution is beautifully described by the physics of the Saha and Boltzmann equations.
So because the temperature's in control, we can do the math.
Exactly. Because the temperature is in absolute control, scientists can look at an LTE plasma and calculate its attributes with arrogant certainty. They can deduce the exact level of ionization, and they can calculate the stopping power confidently because the energy is balanced and contained locally. The system is closed.
Nature despises clear, simple laws when pushed to the absolute extreme.
Yes, it does.
If LTE is the ordered chaos, what happens when the order breaks? What is NLTE?
NLTE stands for non-local thermodynamic equilibrium, and this is the true unbridled void. It is absolute anarchy in the atomic realm.
Anarchy, how does it happen?
NLTE occurs in plasmas where the density drops just enough that it can no longer trap light. Here, the radiation, the photons of pure energy generated by the heat, manages to escape the battlefield. It bleeds out into the surrounding vacuum, radiating away and stealing incredibly valuable energy from the heart of the system.
So the energy is escaping.
The moment this light escapes, the thermodynamic chain of command is shattered. Temperature is no longer the supreme dictator because the system is constantly bleeding energy to the outside. The elegant, comforting equations of LTE completely collapse.
The math stops working.
The distribution of particles becomes aberrant and chaotic. To even guess what the plasma is doing, physicists have to abandon simple temperature models and rely on nightmarish, complex rate equations that try to balance millions of individual quantum collisions against the constant hemorrhage of escaping light.
The plasma becomes unordered.
Yes. The matter no longer dances to the steady rhythm of temperature. It thrashes to a broken, dissonant, unpredictable beat.
And here lies the pure, unadulterated terror of the mission for the people sitting in the control rooms of these experimental reactors. I want you to listen closely to this. Understand the razor's edge these navigators walk.
It is a terrifying responsibility.
Because if our scientists look at the diagnostic monitors and they cannot determine with absolute certainty whether the plasma burning inside the vacuum chamber is obeying the laws of order, LTE, or the laws of the abyss, NLTE, they are effectively flying blind.
Completely blind.
If they are blind to the thermodynamic state, they cannot accurately calculate the ionization level of the particles. And if they cannot calculate the ionization, the entire equation for stopping power is rendered completely useless.
And we know what happens next.
Right. If that ballistic calculation is off by even a fraction of a single %, the laser pulse or the heavy ion beam will strike the deuterium pellet incorrectly. It will fall short, depositing its heat too early, or it will pierce it cleanly from side to side like a ghost.
The compression wave will fail catastrophically.
The spark will be drowned out by the cold void. The miniature star will agonize and die before it emits its first breath of light. The heroic effort of thousands of minds, the decades of research, the billions of dollars invested in steel, superconductors, and hope, it all fails in a nanosecond.
That is the tension they operate under. That is the tightrope of the Lawson criterion stretched across a quantum darkness.
It's just staggering.
It is a level of intellectual heroism that truly demands reverence. We aren't talking about soldiers wielding swords and shields. We're talking about human minds wielding an almost impossible amalgamation of knowledge.
To even attempt it requires everything we have.
Yes, to even attempt this, we have to seamlessly fuse the most esoteric branches of atomic physics, the unforgiving laws of high-density thermodynamics, and the shifting, deceptive shadows of quantum mechanics. Our scientists and reactor operators are fighting a real-time, grinding battle against entropy.
Against entropy itself.
Against the universe's natural, crushing tendency to drag all structure and heat toward cooling, chaos, and ultimate death. Every single spark of fusion that we manage to sustain, even if only for a fraction of a second inside these reactors, is a Pyrrhic scream of victory against the cold silence of deep time.
We have spent this hour traversing the fire. I want you to stop for a moment and just contemplate the overwhelming majesty, the sheer audacious scale of what humanity is attempting. We are mapping the chaotic, invisible currents of the fourth state of matter.
The plasma.
We are forcing supercomputers to calculate the infinitesimal drag, the exact electromagnetic friction of individual electrons that no human eye will ever see. We are fighting desperately to bleed the speed from hyper-accelerated atomic projectiles. And we do all of this for one singular, beautiful purpose: to ignite a microscopic star, hold it captive on Earth, and use its light to power our civilization.
It is, without a doubt, the greatest expression of defiance our species has ever hurled against the darkness of the universe.
And with that defiance echoing in the chamber, I want to leave you, our listener, alone with one final provocative thought. A spark to let burn in your own mind long after this deep dive ends. We have spent this entire journey dissecting how we force a magnetic ocean of plasma to slow down an ion. We've looked at how we maximize stopping power to break the projectile's momentum, forcing it to surrender its kinetic fury to ignite a fusion fire.
We have obsessed over the act of breaking.
We have. But turn the mirror around. Look out at the vastness of the cosmos. Out there in the deep black, the real monsters of the universe, the supermassive black holes devouring entire star systems, the cataclysmic supernovas tearing themselves apart in their final death throes. They operate on these exact same principles.
The exact same physics?
They are fueled by immense magnetic plasma fields. But they don't use these fields to slow matter down. They use them in reverse. The universe uses the turbulent electromagnetism of the plasma abyss to accelerate ions.
To unimaginable speeds.
Whips them up to velocities that brush against the absolute speed limit of light itself, firing them out across the galactic void as devastating cosmic rays. If today, in our humble subterranean cathedrals of steel and superconductors, we manage to unravel the deepest secrets of stopping power, if we successfully map the cosmic friction of the plasma state and subjugate it with mathematics and human will, isn't it logical to assume we could eventually apply the lesson in reverse?
That is the dream.
Could a perfect understanding of resistance become the master key to infinite acceleration? Is it possible that the fusion reactors we are struggling to build today, the ones fighting just to spark a miserable, fleeting light on Earth, will become the architectural blueprints for the stellar engines of tomorrow?
It is entirely possible.
Imagine colossal plasma drives, roaring with the harnessed power of the fourth state of matter, using perfectly calculated magnetic wakes to accelerate heavy ions to the speed of light. Engines capable of propelling the arcs of humanity away from this rocky cradle, crossing the intergalactic abyss to seed our defiance among the stars themselves. The physics are identical. The plasma is exactly the same. The only thing that changes is the scale of our ambition. Think about it.